So, hello everyone, and welcome to the frontiers of parameterized algorithms. I'm very delighted to introduce our speaker of the day, Martin Grohe, who will speak on polylog parameterized algorithms for the graph isomorphism problem. Welcome, Martin, please.
Okay, hi everybody. Yeah, it's a long title. I won't even attempt to read it to you. So I'll speak about graph isomorphism, mostly about recent work we've been doing with these guys down there, Daniel Neuen, Pascal Schweitzer, and Daniel Wiebking. But since this is a seminar on parameterized complexity, I thought I'd start with a slide on parameterized complexity so that at least I have an alibi to be here. Okay, so what I will talk about is what I call polylog parameterized algorithms. And these are algorithms running in time n to the polylog k, where n is the input size and k is the parameter. And one thing you should note, so what this means is n to some polynomial in log k, right? And I will use this notation throughout. What you should note is that this is incomparable with FPT. So for example, an FPT time like 2 to the k times n is not in n to the polylog k because it's strictly exponential in k. On the other hand, something like n to the log k is not FPT. Okay, so we're really talking about something different. As far as I know, such algorithms have not really been studied. And that's probably because there are no natural examples of such algorithms, so why should we study them? Now, as we will see, graph isomorphism gives us a few examples. And I think it's a natural class to study. It's a reasonable running time to look at. However, before you get too excited, let me just point out that all the examples may vanish at once if we find that graph isomorphism runs in polynomial time. But for the time being, I think it's somewhat interesting to look at these. Certainly for the specific problems and in the context of graph isomorphism, it makes a lot of sense to look at such running times. And they are somehow linked to FPT algorithms for the same parameterizations, but the picture is still a bit unclear. Okay, graph isomorphism. So the graph isomorphism problem is to decide if two given graphs are isomorphic. Now you can look at these four graphs, and I suggest you take a screenshot now. And when my talk gets too boring, you can figure out which of these are isomorphic and try to find isomorphisms between them. Okay. And just something I wanted to mention right away, the graph isomorphism problem is equivalent, polynomial time equivalent to what I call the automorphism problem, where we want to find a generating system for the automorphism of the graph. Okay, so these problems are equivalent, and very often when we try to solve graph isomorphism, we will actually look for algorithms solving this automorphism problem. Okay, very briefly, the status of the problem. I don't want to spend too much time on this. I've given so many talks where I had a long general introduction to the problem that I guess many of you have seen me talk about this. So very quickly, let's go over this. GI is one of the very few natural problems in NP for which we don't know whether they are NP time or NP complete. And that's still the case, and it's still open, and it's a very well-known open problem. For example, it was mentioned in Karp's well-known paper on NP complete problems, or also in Gary and Johnson. It's one of, I think, 2 problems that is still open from Gary and Johnson. Actually, it was studied, the computational problem was studied first in the literature on chemical information systems. People represented chemical molecules as graphs, and then let's say they had a database of molecules, and they found a new one, and they wanted to match it against their database. And one of the earliest papers I know is a paper from 1957 that appeared actually in Science and was by people working in chemistry. Okay. In the computer science literature, it first appears in the 1960s. But the big result that we have seen recently is that graph isomorphism is solvable in quasi-polynomial time. That's Babai's result from 2016. I will speak a little bit about this result later. What we also know, and this has accumulated over many years, that GI is in polynomial time for many natural graph classes, including planar graphs and graphs of bounded degree and graphs with excluded minors and excluded topological subgraphs and interval graphs and many more. Okay. We also know a few FPT algorithms. A very nice result was by Daniel Wiebking and a couple of others in 2014, that it's in FPT parameterized by tree width. It's also FPT parameterized by genus, as Ken Kawabayashi has proved. Okay. And that's pretty much what we know there, I think. At least these are the most important examples. And the last thing I want to mention, that in practice, we can solve graph isomorphism fairly well, and we could do this for a long time. Basically, McKay came up with this naughty algorithm in 1980, and that was already very good and continued to develop. It is still one of the best algorithms. And usually for graphs you find in practice, you can solve it. So the interesting part is really this theoretical question, whether it's in polynomial time or not. Okay, let me mention two very important results, both important for what I'll talk about today and important for the development of the research on this problem. And the first is a theorem by Lux, which says that graph isomorphism can be solved in time n to the big O of d, where n is the number of vertices of the input graphs. I always use n for that, and d is the maximum degree of the input graphs. In particular, graph isomorphism is in polynomial time for classes of bounded degree. Okay, let me also mention that a little later, this was improved to n to the big O of d over log d using some advanced group theory, but nothing happens that goes below this, at least nothing happens for a long time. And then of course there's Babai's result stating that GI can be solved in n to the polylog n. Okay, I'm sure you've all heard of this. Now, note that Babai's algorithm doesn't improve Lux. So if the degree of Babai's algorithm is not better than n to the log n. Okay, and this is something we looked at, and a result we proved 2 years ago with Pascal Schweitzer and Daniel Neuen. Graph isomorphism parameterized by maximum degree is polylog parameterized, so PLP. That means it's solvable in time n to the polylog d. Okay, so that's kind of the natural common improvement of Babai's and Lux's algorithm. Okay, and interestingly enough, this result could also be used. We used it first to find a better FPT algorithm for classes of graphs of bounded tree width. And then recently, Daniel Wiebking even proved that graph isomorphism parameterized by tree width is also PLP. That means solvable in time n to the polylog k. Okay. And by the way, I stole some of Daniel Wiebking's slides in particular for the second half of my talk, where I explain our new results. But let me move on here. At the same time, but with different techniques, Daniel Neuen proved that graph isomorphism parameterized by the genus is solvable in n to the polylog of the genus. So the genus of the graph is basically the minimum genus of a surface where we can embed the graph. So for example, if we can draw a graph without crossing on a torus, then its genus would be 2. Projective plane would give us a 1. Okay? And building on these 2 results, we recently proved that GI is parameterized now by the Hadwiger number, as I wrote it there. That's basically the maximum age that KH is a minor of G, or you can phrase it the other way round. It's the minimum size of an excluded minor of G minus 1. Okay, so we parameterize by the minimum excluded minor. That's at least how I think about this. Okay, and there we also have an algorithm in n to the polylog h. Okay, and that's, so mainly I want to talk about this result and this result. And on the way, I also need to go through these. Now, if you look at this, at least those of you, and I've seen quite a few, who have worked with graphs with excluded minors, the guess would be, oh yeah, that's clear. We have bounded tree widths, we have planar bounded genus, and then we use the structural graph theory to get it for excluded minors. Except that this is not at all what we are doing. We're using no Robertson-Seymour structure theory in this result, at least nothing that goes beyond tree width. So mainly the arguments that we use are relying on the fact that graphs with excluded minors have bounded average degree, okay? And well, then we use some structure theory, but it's not the usual stuff. So no excluded grid or anything like that ever shows up in our proof. So that I find quite remarkable, because as some of you may know, I've also worked on this usual structural stuff, which you would expect here. Okay. So that's pretty much my introduction. Now I want to get more technical, and I want to speak about the group theoretic techniques that led to first Lux's and then Babai's result. And then I want to explain you a little bit how we proved our PLP algorithm for graph isomorphism parameterized by degree. Okay. So let me start with a little bit of background from computational group theory. The first fact is that every group has a generating set of at most logarithmic size. It's a simple group theoretic fact, but it's very important for us because we're talking about automorphism groups of graphs. For a graph of size n, the automorphism group can have up to n factorial members. That's too much. But at least we have a generating set logarithmic in n factorial, and that's fine. That's polynomial in the size of the graph. So we can talk about groups, all kinds of groups that may appear as subgroups of the symmetric group of the vertex set, including the automorphism group. We can represent them, and we can do computations on them. But of course, the question is how we do this. But at least we're not immediately out of the game just because the groups are too large. Okay, the second fact I've already mentioned, GI is polynomial time equivalent to the problem of computing a generating set for the automorphism group. So that's what we set out to do. And then the third fact just collects a few basic algorithmic routines for permutation groups. Okay, and the way we see these, we always represent the groups by generating sets. And then we want to be polynomial in the size of the generating sets. And of course, we want to have an output, which is a generating set again, at least if the output is supposed to be a group. And we must make sure that it doesn't get too large, but that's something we can usually do. We can always make generating sets smaller in a way. Okay, so what are these facts? The first is to compute the orbits of a graph. So what's an orbit? It's basically if we have an element like this one here, it's all elements the groups maps them to. We have a permutation group, so this here is the permutation domain. So we move the elements around, and all places where this red point can be moved is the orbit of the red point. Okay, and the orbits partition the whole set, which for us usually is the vertex set of a graph, and we can compute this partition in polynomial time if we have a generating set for our group. The second thing is we can compute a minimal block system. Now, what is that? It's an invariant, non-trivial, so invariant, non-trivial equivalence relation with the minimum number of classes. Okay, so that probably also doesn't mean so much to you. So basically, what is it? It's a partition of the sets that we permute into sets we call the blocks. Okay, the whole partition is the block system. And then the operation of the group on this block system can be as follows. Well, the permutations can permute the blocks, okay, stay within each of the blocks. So for example, a permutation could move this, okay, now could move an element here to an element here, at the same time an element here to here, and so on. Or it could also move whole blocks, like here. So it can map this whole block to this block. What should not happen is something like this, that a block is mapped to something that is not a block, okay? So this is forbidden, okay? Now, such a block system, a minimal one is one with a minimal number of classes. Of course, the whole set in itself is also just one block, so we always want to have at least 2 blocks, otherwise it's pointless. Okay, so we can compute that in polynomial time. And for example, we can also test membership in polynomial time. Many more things. We can, for example, compute the size of a group from a generating set. We can compute generating sets for subgroups of small index and other things, but I don't want to go into this. Okay, the next thing I want to talk about is an abstraction that is often convenient when dealing with automorphism groups of graphs, because it makes it easier to use recursive strategies. Okay, and in the area, this is known as string automorphism or string isomorphism. Okay, and we can always reduce the automorphism problem to a problem of this type. So we're given a string. Now a string is something you would normally not think of as a string, but anyway, people in this area do. It's just a mapping from some base set, for example, but it can be something else, to a finite alphabet. Okay, a finite set of colors, if you will. Okay, and then we have a group which is a subgroup of the symmetric group on this set, on the domain of our string. Okay, and then aut of xg is to compute the subgroup of this group G, consisting of all mappings that leave the string stable. So the value x of u is always the same as x of the image of u. Okay, so basically in this sense it's automorphisms of the string, but we're only looking for the automorphisms in our given group G. Okay, and this way we can, for example, make the group smaller and smaller. And when we say we want to compute a subgroup, we always mean we want to compute a generating set for this subgroup. Okay, and we can do something similar for 2 strings and isomorphism. And then we're usually given a coset of some group here. Okay, and how does the reduction go? So basically the way we do this, let's say we have a graph like this one here, cycle of length 4. The automorphism group of this graph is a subgroup of the symmetric group on 1, 2, 3, 4, on the vertices of the graph. Okay, and now we define a string, and the domain of the string is just the unordered pairs of elements, and we color the unordered pairs in red if there's an edge, in white if there's no edge. So this here is our string. There's all unordered pairs. There's an edge from 1 to 2 and from 1 to 3, no edge from 1 to 4, no edge from 2 to 3, and so on. Okay. And now the group S4 also acts on this string, and in part, or on the set of unordered pairs. Okay. But it's not the full symmetric group. So not all permutations of the unordered pairs are permitted, but only some. Only those permutations that correspond to permutations of the underlying set 1, 2, 3, 4. We would denote this group by S4. Well, here this indicates that it's acting on the unordered pairs. So that's a subgroup of the full symmetric group of this set. That's our group G. And now basically we just have to find the automorphisms of the graph are basically those permutations in this group that leave the string fixed, that keep the colors fixed. Okay. And the advantage of this, well, there's two advantages. Basically, we can go to smaller and smaller groups. So a general strategy will be, we start with the full symmetric group of all permutations, and then throw away things that are not automorphisms, and then we hope in the end to have the automorphism group. And this formulation allows us to go to smaller groups. And there's a second good convenient thing. If we split such a string somewhere, okay, let's just split it here. Then we can somehow, and let's say these are two orbits of the group or something, then we can look at this part and this part separately, and we don't have to worry about edges that may cross the cut. Whereas if we split a graph, maybe like this, we have these edges across the cut that somehow indicate dependencies between the two parts, so we cannot look at the two parts independently. In the string isomorphism, all the dependencies between the two parts are somehow encoded in the group. That's another reason why it's easier to work with this. Okay, so now let me describe Lux's strategy that he used for his bounded degree algorithm, although on a very high level. So our goal is to compute this automorphism group of a string within some group G. Okay, so we're given a generating group, want to find a generating system for that group. And we can reduce graph automorphism to this problem using the construction I just described. Okay, and the strategy is as follows. If the group is not transitive, which means that it has more than one orbit, then we can compute the orbit, so we can detect this. And what we do is we just recursively process the orbits one after the other. And for any orbit, basically, our group gets smaller and smaller, and in the end, we have the right group. Okay, so that's the first type of recursive step. Now, what if the group is transitive? Well, then we check, is it primitive? And primitive means that it has no non-trivial block system. But if it's not primitive, we can compute a block system. So a partition like this. Okay. Okay, and then what we do is, we compute the block system, And now look at two subgroups. One subgroup that fixes all the blocks, so that just operates within the blocks. Okay, that's a smaller group, so we make progress, that's good. And the second is, we look at the group that permutes the blocks as a whole, but we don't care what happens inside of the blocks. That's also a smaller group, so we can also deal with this. And then we put everything together and we're happy. Now, there remains one bottleneck, that is if we have primitive groups. Okay, and there basically we get stuck. Okay, and the thing is, a lot is known about primitive groups. For example, from the classification of finite simple groups, we can get a lot of information about primitive groups. And that is basically what we want to use, and that's what Lux used and what Babai used to make progress with such a recursive algorithm. Okay, so let's first talk about Babai's algorithm. And a key group theoretic fact that he uses, and that also to some extent explains the quasi-polynomial running time. And this fact says that up to a simple family, of so-called Johnson groups, which are alternating or symmetric groups acting on the k-element subsets of a set. So up to this family, the primitive subgroups of the symmetric group have quasi-polynomial size in n. Okay, and if we're in a group of quasi-polynomial size, we can usually just use brute force to compute all elements of the group, and then everything becomes easy. Okay, so all we need to do is deal with these groups, and that's difficult enough. I mean, Cameron's fact was known since the 1980s, and nobody knew how to do this until Babai found something. So what's Babai's strategy really on a very high level? So he refines this divide and conquer strategy, either finding an invariant subset like an orbit, or finding an invariant equivalence relation like a block system, a minimal block system, or I somehow identify that the structure of the problem is simple, that we have one of these Johnson groups basically, or what he calls a Johnson graph. And all of this is highly non-trivial. So this is really very simplified. But anyway, the first two outcomes basically mean that we can make progress towards a smaller problem. So that's good. So what do we do in the third case? If we have identified this simple structure, well, we have to deal with these highly symmetric graphs and do some very sophisticated symmetry breaking. I don't want to talk about this now. And don't worry, by the way, if you're put off by all the group theory, this will stop in a couple of slides, and then it gets so the groups will appear at some point. So there's hope. I think maybe 3-4 more slides on groups. Okay. So now let's look at bounded degree. So what did Lux do with the primitive group problem? Okay, and what he basically saw is that he can reduce the problem to a class of groups that are much simpler than general permutation groups, and he calls this class gamma D, and that's groups where every composition factor is isomorphic to a subgroup of the symmetric group on D elements. Now, what are composition factors? Let's just say they are building blocks of the group. If you have never heard of them, never mind. It's not so important. So basically what this means is that such groups are built in some way from small groups, bounded in D. Okay, and that's very good. So what looks proved is that if I have a connected graph of maximum degree D, a vertex in this graph, and then I look at the automorphism group of the graph and fix this vertex. So I look at all automorphisms that keep this vertex fixed. Then this group I get is in gamma D. Okay, and why is that? It's very easy to see. So here we have a graph of degree 3. We fix a node. And now we make an observation. So we only look at automorphisms that map V to V. Then they also must map the neighbors of V, this one, and this one, to other neighbors. So basically, every automorphism that fixes V must somehow permute these 3 vertices, map them to one another. So here we only have a symmetric group on 3 elements. Okay, so these 3 are permuted. And now we basically move on in a breadth first search and look at their neighbors. And actually, now it's only 2 neighbors that we haven't seen. So for example, the group must, so now we have something like a block system, the 2 neighbors of each of the 3 nodes. But the bottom line is the next building blocks are the groups permuting the neighbor sets of these. And again, they are small. They are just even symmetric groups on D-1 elements. Okay? And if we move on with a breadth first search, now in this graph, we have already reached everything now. But for a bigger graph, in every step, we somehow decompose the possible permutations into small permutations that just permute the neighbors of some vertices. Okay, and that's what is underlying this lemma. Okay, and once we have this, now that means the primitive permutation groups appearing in such graphs are also small. Okay, and when they are small, where basically we can reduce graph isomorphism from maximum degree D to string isomorphism for gamma D groups. For the gamma D groups, all primitive groups appearing within these groups are small, and that's why we get, with the divide and conquer strategy, immediately n to the f of D. And now, if we're a bit more clever looking at these groups, we can actually bring it down to n to the D, or even n to the D over log D. Okay, so what did we do to bring it down to n to the polylog D? Okay, so our goal is n to the polylog D. Oh, come on. So the first thing we did is we looked closer at these gamma D groups and used some heavy group theory to basically show that they have a reasonably nice structure. Basically, what we have is a decomposition here of these groups into some kind of tower of small groups, and small for us is n to the polylog D. Alternating groups am for some m at most d. Okay, so that's the structure of the groups. And now we use a trick that I think is new and quite nice. Here we now have a string x and a gamma d group, and we want to, from this, we construct a slightly larger string and a tree on top of this string. And this tree encodes the structure of the group as we obtained it here. The group has some hierarchical structure, and basically the nodes of the tree correspond to the subgroups appearing there in some way. Okay, and the construction is completely canonical. So the resulting structure still has the same automorphism group. But now we have this explicit encoding of the group there. And then we can just work our way along the nodes of the tree. And we have nodes corresponding to alternating groups here. For these, we use Babai's techniques. And we have small groups. And for the small groups, we can use brute force. Okay? And that's all I can say about this now. And here we are leaving group theory and we move on to graphs with excluded minors. Okay, and now I think we're coming to more familiar territory, and we start with decompositions, and actually tree decompositions, and with Daniel Wiebking's result that I mentioned on one of the first slides. Okay, but our starting point here is another result we proved with the two Daniels and Pascal Schweitzer, and that was for an improved FPT algorithm for graphs of bounded tree width. And what we showed there as a technical lemma is that we can find an isomorphism invariant tree decomposition of a graph of tree width at most k, such that the adhesion of this decomposition is bounded by k, so the overlap between two bags. The bags themselves can be large. However, on each bag, we can find an isomorphism invariant structure of bounded degree, and the degree is bounded by polylog k. Now, this is vague. What is an isomorphism invariant structure? If we want to make this precise, we basically say we find a gamma k or gamma poly of k supergroup of the automorphism group of these graphs, but actually we construct something of bounded degree. So we reduce the tree width problem to bounded degree, which I think is quite interesting, which I haven't seen before. So we have this structure and we can compute everything in polynomial time. Okay. And now let's see how we use this to get such a PLP isomorphism test for graphs of bounded tree widths. And that's the new results by Daniel Wiebking that appears in this icon. Okay, and the strategy is, well, first we compute the tree decomposition I described on the previous slide with the structure of bounded degree on the bags. Okay, and then we use this bounded degree structure on the bags to compute the sets of all isomorphisms between all bags of the graphs G and H. Okay, we can do this because we have this bounded degree structure. And then we somehow have to merge the isomorphisms. Now, steps 1 and 2, we already knew in 2018 when we wrote this other paper, but we didn't know how to do this. So basically, we're in a situation like this. We have a bag here and a bag in the other graph here. We have some stuff hanging from this bag, and we can somehow compute isomorphisms on these parts here. Okay. So let's say we define these sets. Lambda ij is the isomorphism from this part here. Let's say if 1, 2 would go from here to here. Okay? We can compute them. No. Let's say we have them from our recursive algorithm or dynamic programming algorithm. Okay? So then when we want to merge them, of course we can forget everything that comes in position. We only have to look what is induced on V and W. So these induce some isomorphisms on V and W, because if I go from this whole thing to this whole thing, it also does something here. And somehow we must sort things on these blocks out that somehow we have a good matching between the parts below. So for example, if we look at the intersection of lambda 1, 1, so everything that maps the first to the first, lambda 2, 2, second to second, third to third, that would be precisely the isomorphisms of the whole graphs that map AI to BI. Okay, and we restrict everything to the set V here because we don't care what happens below V if we move up in the dynamic programming. So the problem we need to solve is somehow we have two sets, V and W. We have some sets of mappings, lambda ij, which we get out of the dynamic programming. And then we have to put these together in a consistent way that we have a matching between the i's and the j's. So there exists a matching between the i's of the j's such that everything fits, okay? And that we have to calculate out of these sets. That's the problem we need to solve if we want to merge, and that's a difficult problem, but Daniel solved it, okay? And this implies that GI parameterized by tree width is solvable in a time n to the polylog k. Now, I'm getting to a hot topic in current times, which you may not recognize immediately, but will in a minute. But I start with an algorithm that appears in all of my talks, the color refinement algorithm, or one-dimensional Weisweiler-Liemann algorithm, and that computes a coloring of the vertices of a graph. Okay, sorry for all those who have seen me give this slide many times, but let me just explain the algorithm for those who haven't. So the input to the algorithm is a colored graph, or if it's uncolored, we just say all vertices have the same color, okay? And then we go into a loop, and in each iteration of the loop, we check for all nodes that still have the same color. Is there some other color such that they have a different number of neighbors of that other color? Then they get different colors. So the partition induced by the coloring gets finer and finer, and at some point it must stop because we have finite graphs. And that's actually after at most n steps because we have a partition of n elements. And when it stops, we say the coloring is stable and return the coloring. That's what color refinement does. And let me show you this demo by my student Erkal Sellmann. So here we just have some random graph, and initially here all vertices have the same color, blue. And now if we look, for example, let's see, this vertex, the one I'm pulling there, has 2 neighbors. This one has 3 neighbors, though, so they should get different colors. And yay, they do. The 2 neighbors is orange, the other 3 neighbors is now purple. Now let's look at this one and its neighbor. Both purple, but they have, this one here has a green neighbor, this one doesn't. So they should get different colors in the next step. And they do, okay? These 2 shades of green. Okay, and now let's group the vertices by color and just move on, and the color classes get smaller and smaller. And at some point, here they get really small, we're stuck. Okay, we can play this once more. So initial coloring, and we get smaller and smaller and smaller, and that's the stable coloring. So for example, interestingly, no, these brown vertices, we have different browns here. That sometimes happens. Anyway, okay, so that's how it goes. Extremely simple algorithm, also can be implemented very efficiently, running in time n log n. We can run it on a graph where basically all vertices have the same color, that's the default, or we can start with some coloring and refine this, and then we compute in a way the coarsest stable refinement of this color. Okay, and now we want to talk about spreading an infection. So that's an extended algorithm, and goes as follows. We can individualize vertices in a colored graph, and individualizing vertices means we assign fresh colors to these vertices. So I individualize a vertex, that means I give this vertex a new color that appears nowhere else, and all other vertices keep their colors. Okay, and then our algorithm is the following. We start with a colored graph, and we have a parameter which is a positive integer t. And then we repeat the following 2 steps. We apply color refinement. So we compute a stable coloring, refining the current color. And then we look at all color classes that have at most t elements, okay, at all small color classes. And we individualize all vertices in all these color classes, okay? Okay, now we have a new coloring, a finer coloring. We apply color refinement again, make it stable. Color classes get even smaller. We individualize again, and so on. And we do this until the coloring no longer changes. Okay, and we say a vertex is infected if its color class in the final coloring has size 1. Okay, let's see an example. So here's a very simple one. We have a path of length 6, and we take our parameter t to be 2 here. Okay, so first we apply color refinement, and color refinement does the following on this graph. Okay, that's not difficult to see. You can just play the game. Basically, the colors evolve from the endpoints, which have degree 1 to the middle. Okay, so now we have 3 different color classes, but all have size at most 2. So great. When we individualize everything in all these color classes, and now every vertex is infected because all color classes have size 1. Okay, second example, slightly more complicated. We start by running color refinement. So now we have on the path, we have still 3 color classes, the same we had before, but then these feet attached to the path also get their own colors. Okay, so now the color classes of size 2 we individualize. That's only the color classes on the path because all others have size 4. Okay, so we split them. Now we're in this situation. We run color refinement again. So now the coloring on the feet also changes. Looks like this. Now all color classes have size 2. We individualize again, and everything is infected. Okay. So in this graph, all vertices are infected after the second round. Okay, and we play this for as long as we can. Okay, here we have a graph, cycle of length 6, where nothing happens. Color refinement will do nothing because all vertices have 2 neighbors, so 2 blue neighbors, so nothing happens. And so there are no color classes of size at most 2, so basically nothing, no vertex will be infected here. Now what we can do is we can induce an infection. We can individualize one vertex and then see how the infection spreads from this vertex. So let's do this. We color this vertex red here. That's what individualizing means. And then we refine, and the refinement looks like this now. Now we have color classes of size 2. When we individualize again, all classes have size 1, everybody's infected. Okay, so that's our algorithm, and it's a fairly powerful algorithm. Okay, and let's say a graph or colored graph is T infected if all its vertices get infected. Okay, so for example, the cycle with 1 red vertices would be 2 infected. Okay, and an interesting observation is that every connected graph of maximum degree at most T plus 1 gets T infected once we individualize one vertex. And that's connected to what I told you about before for the bounded degree graphs. We start with one vertex. Okay, let's see. We have our graph here. We start with one vertex. That's the first one. That has its own color. Now it has some neighbors. This doesn't work very well. So 3 neighbors, say. Okay. So, okay, actually I should say maximum degree T. I made a mistake there. Okay, so we have the 3 neighbors. Now if I do color refinement, this one here already has a special color like this blue-white. Then these 3 will end up in will end up in their own color class, maybe even smaller, but we certainly have a color class of size 3. So in the next round, these will all get individualized. So they may get colors like this. So what else can I put? Okay. And now as this spreads, all vertices get infected. Okay. So this is certainly, if we allow individualizing a single vertex, and in the end we can always do this, we can try all possibilities. This includes all graphs of bounded degree. And what Daniel Neuen proved is that isomorphism for these T-infected graphs parameterized by T can be decided by a PLP algorithm. Now, this idea of the algorithm, that was around for a long time in minor variations. Okay, but of course, this polylog parameterized algorithm that was new and also not easy to obtain. But I can't tell you how it's obtained. It's basically building on the bounded degree work. Okay, and Daniel actually proved a little more that will be important for us, that somehow when this infection spreads, it transmits structure of bounded degree, or it transmits these gamma D groups, if you will. So that means, let's say we start with some set, and on this set we have a structure of bounded degree, here a graph of degree 3. Then if we let the infection spread, in the end we can get such a structure on the whole graph or on all graphs that are reached by the infection, okay? And for these graphs, and that's in a way the idea to prove the previous theorem, but it's also useful in its own right. Now, as far as the infection spreads, we have this bounded degree structure if we can start with a bounded degree structure. Okay, now let's move on and finally prove the result on graphs excluding small minors. So remember, Hadwiger number was the largest complete graph that is the minor of our graph. And the theorem we want to prove is that we have an isomorphism test in time n to the polylog of the Hadwiger number. Now we put together this infection spreading technique and the decomposition technique. So first we prove a decomposition theorem, or that's in a way the main thing we need to prove. And it says it's basically the same theorem that we had before for tree width. Now it's for a graph of Hadwiger number Hadwiger number at most h. There is an isomorphism invariant tree decomposition. The adhesion is bounded by h. And on each back, we can find an isomorphism invariant structure of degree polylogarithmic in h. So before, instead of Hadwiger number, we had tree width. Other than that, exactly the same theorem. And again, we can compute everything in polynomial time. Okay, so that's what we proved. And once we have proved this, we can use Daniel Wiebking's decomposition results to prove the theorem. Okay, so we need to get this decomposition. How do we get this? Well, we use this idea of spreading an infection. And if we reach the whole graph, we somehow know we win. But sometimes we can contain the infection, so it stops, like here. Okay, so it spreads, but then at some point it stops. And the lemma we prove is that the infection can only stop at separators of size strictly less than h. Okay, so here we have these small separators. That's where it stops. Okay, and I can also show you the formal statements. So let's say we have a colored graph of Hadwiger number h. We say t is 3 times h to the third. We look at the set of all t-infected vertices. Then for every connected component of the graph without the infected vertices. For example, this part here or this part here, the number of neighbors is strictly less than h, the Hadwiger number. Okay, so this in a way gives us the decomposition. Now we need the bounded degree structure on the banks. And to get this, we somehow must find a point where we can start the infection, from where we can move. And that's the main remaining thing we need to prove. We can compute an isomorphism invariant set. On this set, we have a bounded degree structure, as you see here. Now, if we individualize a single vertex of this set, then all vertices of the set get infected, and actually probably some more. But then we know from Daniel Neuen's result that also on all the vertices that get infected, we have this bounded degree structure, and that's precisely the bounded degree structure we need for the backs of our decomposition. Okay, and that's how we prove this, and that's pretty much all I want to say. I thought I close with a few open problems. First one is very well known. GI parameterized by maximum degree is at FPT. We have this polylog parameterized algorithm, but we don't have an FPT algorithm, which is annoying. And I've thought about this for a while, but I have no idea. The second is GI parameterized by Hadwiger number FPT. Again, we only have this polylog parameterized algorithm. That seems more feasible to me at the moment, but I also don't know how to do it. The third is if instead of minus, we exclude topological subgraphs. We know we have a polynomial time algorithm then, but we neither know FPT nor polylog parameterized. And actually, if we look at our proof for excluded minors, most of it goes through for excluded topological subgraphs, but not everything. Essentially, the last result does not go through, the last lemma. Okay, and anyway, that's all I have to say. I'll be happy to take your questions or remarks.
Thank you very much, Martin. Questions, please. So maybe a naive question. This is I miss. So for your GI algorithm, do you need to know the Hadwiger number?
No. Basically these things all come out, and I don't need to know it. I mean, I can just basically I can run the algorithm for all possible Hadwiger numbers, and if I find the right structure, then I win.
So maybe I can ask a question as well. To what extent does this work for canonization problem?
I think it will work, although I mean, it's always additional work. I'm sure Daniel Wiebking will work this out. Actually, I don't know if it works immediately. It seems to me that this should work with only technical effort, but I'm not completely sure. I've never thought that much about canonization. Maybe Daniel Neuen, I've seen, was there. He may be able to say that. But yeah, I don't know. I would guess it shouldn't be a problem.
I see, thanks.
I mean, maybe I can add something here. So I think it might really be non-trivial. So I also don't know how this goes. I mean, the thing is that also for Babai's algorithm, it took some effort to generalize this from GI to canonization. And I know there are some problems there that he had to solve, but I'm not completely familiar with these things.
But
so obviously
Daniel,
we have to do these.
Daniel Wiebking, for his stuff, he has canonization, doesn't he, in his iCalc paper?
Yes, but he only at these places uses Babai's things as black box.
Oh.
And I mean, we open up the algorithm of Babai
okay.
to some extent.
Yeah, I don't know.
So, yeah.
Oh, hi, Professor Grohe. Thank you for the talk. Yeah, recently I read several of your papers about this topic. I'm very impressed by your work with the connection of GI and like logic and Strali item hierarchy, and also like a graph homomorphism. Yeah, it's quite surprising you can find so many deep connections with some other areas. Can you talk a little bit more about the connection of your current work and your talk today with those areas?
Okay. Yes, I mean, there's this is something I've done a lot. That's this so-called Weisweiler-Liemann algorithm, which is a combinatorial algorithm that generalizes the color refinement algorithm that I've shown you here. It's instead of coloring vertices, we color tuples of vertices. And it's known that this doesn't decide isomorphism, but that has many, many connections to other things like counting homomorphisms, certain systems of linear equations, also to logic and all that. And something I've also always been interested in is whether this is the complete algorithm for a certain class of graphs. And we've defined the notion of Weisweiler-Liemann dimension, which is, in a sense, for a graph, the least d such that the d-dimensional Weisweiler-Liemann algorithm characterizes this graph. So for many graphs, we know at least bounds, and that excludes all graphs with excluded minors. So what we also know is, well, we have this algorithm with this polylogarithmic exponent, but we have also a p-time algorithm, which is an extremely simple combinatorial algorithm, no group theory at all, which is also nice. Now, we also know that for bounded degree, this algorithm is not good enough, even for degree 3. And some things, for example, we are thinking about, and I've been thinking about for a long time, is whether we can strengthen the combinatorial approaches. Now, for example, this infection strategy, in a way, is a strengthening. It still has a very combinatorial flavor, but it has this non-trivial group theory part, which you almost don't see. But then once you realize all bounded degree graphs fall under this, you know something non-trivial is going on. So these are always things I'm thinking about. Well, make any very explicit connection between this work and some other work on Weisweiler-Liemann I have done.
Thank you very much.
Doesn't seem to be any other questions. Then thank you once again, Martin. And see you someday.
Yes.
Yeah. Thank you.
Okay.
Goodbye.
Thanks everybody for coming, and okay, goodbye.